Assalamualaikum warahmatullahi wabarakatuh. A very good day to all of you. So for chapter number 5, we will discuss about the refrigeration cycle, where in this chapter we discuss the specific thermodynamic cycle for the refrigerator, and we will learn about the TS diagram, about the schematic diagram, and also the formula that involved with the refrigeration cycle in terms of performance of the refrigerator. Okay, so these are the subtopics that we learn in this chapter. First, we discuss about the introduction of the refrigeration, and then we discuss the reverse Carnot cycle, the most called the highest performance in terms of thermal cycle for the refrigeration, and then we discuss about the ideal vapor compression of fusion cycle, actual vapor compression of fusion cycle, and then we will discuss about how to use the pressure enthalpy diagram, and the last one is about the innovative vapor compression refrigeration system. Okay, if you look at this chart, so under power generation, we already done our call to learn or to discuss about the thermodynamic cycle that involve with power plant, and also the thermodynamic cycle that involve with internal combustion engine. So now for chapter number 5, this chapter actually is under the cooling and also heating system categories. Okay, now we will start our discussion with the introduction about the refrigeration system or refrigeration cycle. Okay, the introduction of the refrigeration. So the figure shows the cross section called 2D drawing for the refrigerator. Okay, so we can see that if you look in the schematic diagram or in the figures, there are a few important parts that involve with the refrigeration or refrigerator system. First, we have expansion valve or expansion device, evaporator coil, compressor, and also condenser coil. So later on we will discuss into detail the function for each component in the system. Okay, so the device for the refrigeration system we call refrigerator, and this application is one of the major application of thermodynamics. And the main function of the refrigeration system or refrigerator is we want to transfer heat from the cold area by using the refrigerator and transfer the heat to the hot area. So we absorb heat from the cold area by using a device that we call refrigerator, and then transfer the heat to the hot area. So that the main function of the refrigeration system, or the main function of the refrigerator. Okay, so we have cold area or refrigerated space in the refrigerator. The evaporator will absorb heat from the cold area, so that the temperature of the cold area, or the temperature of this refrigerated space will reduce, so that we can keep our foods, drink, and so on in the refrigerator. And then the refrigerant inside the refrigeration system will transfer heat to the surrounding through the condenser coil, as shown in the figure. Okay, so the surrounding we consider as the hot area. So in terms of thermodynamic cycle for refrigeration, there are two types of cycles. First, we have vapor compression cycle, where in this cycle we will use refrigerant or working fluid that change in terms of phase throughout the process. So sometimes the working fluid or the refrigerant will be in compressed liquid region, or saturated mixture region, or superheated vapor region. However, the second cycle is the gas refrigeration cycle, where in terms of working fluid or refrigerant, in terms of phase, the phase along the way will be only in gas phase. Okay. However, in our discussion in chapter number 5, our concentration, our focus only we discuss about the vapor compression cycle. Okay, we will not discuss about the gas refrigeration cycle. Okay, now we look at what the difference between the refrigerator and also heat pump. So actually, the refrigerator and also the basic concept and also the general knowledge in terms of refrigerator and also heat pump, you already learn in thermodynamic 1. Okay, so now I just want to refresh again what you have learned and add some more information about the refrigerator and also about the heat pump related to the chapter number 5. So the refrigerator and also the heat pump, actually both devices will use the same system, where this system, the function of this system is to transfer heat from low temperature to the high temperature area. Okay, so in terms of basic system for the refrigerator, the refrigerator consists of evaporator, compressor, condenser, and also expansion valve. So these are the basic main component for the refrigerator. However, if you look to the heat pump, main component also will use the same main component, same as the refrigerator, where the heat pump also will have evaporator, compressor, condenser, and also expansion valve. Okay, for the refrigerator, in the refrigerator, the system where the evaporator will absorb heat from the refrigerator, so that the temperature inside the refrigerator space in the refrigerator will reduce, so that we can keep our food, our drink in the refrigerator for the longer period of time. So then the refrigerator that absorbs heat will transfer heat to the surrounding through the condenser. Okay, so these are the process that occur in the refrigerator. So if you look at the heat pump in terms of process, so the evaporator for the heat pump will absorb heat from the cold surrounding, and the refrigerant inside the system of the heat pump will release heat into the house through the condenser, so that the temperature inside the house will increase. Okay, so now we can see that both refrigerator and also heat pump will use the same system, but in terms of application will be different. So for the refrigerator, the function of the refrigerator is to maintain the refrigerator space at low temperature by removing heat, as shown in this diagram. So we can draw the simple simplified schematic diagram to describe the process in the refrigerator, where the circle with R symbol represent the refrigerator. Okay, the circle actually represent the refrigerator that consists of the main component in terms of compressor, condenser, expansion valve, and also evaporator. Okay, so we just simplify this diagram and just draw the circle with R symbol. Okay, so for the refrigerator, we need to supply W in, W net in, where we consider W net in as required input because we need to supply W in to the compressor. Okay, so the evaporator will absorb heat from the cold refrigerator space, and the amount of energy that absorbed by the refrigerator from the cold refrigerator space represented by QL, and we consider the value of QL is the desired output. And then the heat from the refrigerator will release through the condenser, and the amount of heat released to the warm environment represented by the value of QH, as shown in this diagram. So these are the process involved with refrigerator. In terms of performance for the refrigerator, we can determine the performance by calculate the value of COPR. So COPR represent the coefficient of performance for the refrigerator, where COPR equal to desired output divided by required input, which is also equal to cooling effect divided by W input. So in terms of symbol, COPR also equal to QL divided by W net in. So these are formula that can be used to determine the performance of the refrigerator. However, in terms of I call the function or the function of the heat pump, if you compare to the refrigerator, so heat pump, the function of the heat pump is you want to maintain a heated space at a higher temperature by absorbing heat. Okay, where the heat pump will absorb heat from the cold surrounding air and then release to the heated space. So if you refer to the schematic diagram, refer to the area inside the house. Okay, so if you draw the simple schematic diagram, so the heat pump represented by the circle with HP symbol, and the symbol also represent the what I call the main component of the heat pump, where we have the compressor, condenser, expansion valve, and also evaporator. So same as the refrigerator, the heat pump also we need to supply W net in, where this W net in we consider as required output, and the heat pump will absorb heat from cold environment, that represented by the value of QL, and then the heat pump will release the heat that represented by QH, which is also referred to the desired output, into the house in order to increase the temperature of the area inside the house. Okay, and in terms of performance for the heat pump, so we can calculate the performance for the heat pump by using this formula, where COPHP equal to desired output divided by required input, also equal to heating effect divided by W input or work input, and COPHP also equal to, if we use the symbol in the schematic diagram, COPHP equal to QH divided by W net in. So if you combine in terms of COPR and COPHP, we have another equation that relate both COPR and also COPHP, and this equation actually you already learned in thermodynamic 1, where COPHP equal to COPR plus 1. So these are what I call the differences between the refrigerator and also the heat pump. Okay, now we will discuss about the thermodynamic cycle for the refrigeration system. So the first thermodynamic cycle that we will discuss is about the reverse Carnot cycle, which is the highest performance refrigeration cycle. Okay, the reverse Carnot cycle. So the reverse Carnot cycle, in order to discuss about the reverse Carnot cycle, let we look at this schematic diagram. So this schematic diagram represents the schematic diagram for the reverse Carnot cycle, where we have a compressor, a condenser, a turbine, and also a evaporator. So these are the main component for the reverse Carnot cycle. In terms of state, we will have 4 states involved, state number 1 until state number 4. Okay, so the function of the compressor, so the compressor will compress the refrigerant inside the cycle. So we'll have isentropic compression process from state number 1 to state number 2. The second process involved is the condenser, where the heat released to the environment or to the warm medium at TH from state number 2 to state number 3 at constant pressure. So we have in the condenser we have heat rejection at constant pressure, and then the refrigerant will experience expansion process in the turbine. So where in the turbine we will have isentropic expansion process from state number 3 to state number 4, and then further the refrigerant will go through the evaporator, where the temperature is at TL. So the evaporator will absorb heat from the cold medium at TL at constant pressure. So these are 4 processes involved for the reverse Carnot cycle. Okay, so if you draw the process on the TS diagram, so we have called the square shape cycle for the reverse Carnot cycle. So we have 4 states involved, state number 1 until state number 4, and also we have 4 processes involved. Process number 1 involved is isentropic compression in the compressor from state number 1 to state number 2. So S2 will be equal to S1. Process number 2 will be heat rejection or heat release from the condenser to the warm medium or warm environment at TH, and the value of energy that released represented by the value of QH. So the process involved start with state number 2 to state number 3. So for process involving state number 3 to state number 4, so the process involved with the isentropic expansion process in the turbine where S3 equal to S4. And the last process involved with heat absorption or heat addition. So for the this process involved in evaporator, where the evaporator will absorb heat at constant pressure from state number 4 to state number 1, and the energy that absorbed by the evaporator represented by the value of QL. Okay, so this is how we describe the reverse Carnot cycle by using the TS diagram. So the reverse Carnot cycle actually is the cycle with highest performance for a refrigerator and also for a heat pump. So if we determine the performance for the Carnot refrigerator, we can determine the performance in terms of COP value by using this formula, where COPR for the Carnot cycle equal to 1 divided by TH over TL minus 1. However, for the Carnot heat pump, the COP value for heat pump for the Carnot cycle can be used we can determine by using this formula, where COPHP Carnot equal to 1 divided by 1 minus TL over TH. However, the reverse Carnot cycle is actually not practical for the actual application of the refrigeration cycle due to few reasons. So the first problem or first reason is involved with process from state number 1 to state number 2 if you refer to the TS diagram. So this process involved with the isentropic compression process in the compressor. Okay, so if you look at the TS diagram, state number 1 in terms of phase is in saturated mixture, which means what I call the refrigerant will be in terms of phase will have 2 phases, in liquid phase and also in the vapor phase, and state number 2 in saturated vapor. So throughout the process from state number 1 to state number 2, the compressor have to compress different type of phases in terms of refrigerant. Okay, different type of refrigerant phases. So this is the problem, because normally the compressor only handle one phase of the refrigerant, okay, which is referred to the vapor phase. However, for this case, the compressor need to handle 2 phases, which is liquid and also vapor. So this is not practical and also not good for the compressor. Okay, second reason or the second problem involves is the process in the turbine. The process during the isentropic expansion process start from state number 3 to state number 4. So if you look at the process in TS diagram, the expansion process will involve the high moisture content refrigerant. Okay, so if you look at the inlet of the turbine will be at saturated liquid, and at the outlet of the turbine will be at state number 4, the refrigerant will be in saturated mixture region. So which means along the expansion process, the moisture content keep increasing during the expansion process in the turbine. So this is the condition is not good for the turbine blade during the expansion process. So the high moisture content will damage the blade during the expansion process. Okay, so we have low vapor quality and also high moisture content for the problem number 2 for the process 3 to 4 to the expansion process. Okay, so that's why the Carnot refrigerator or the reverse Carnot cycle that we apply to refrigerator is not practical due to this reason. So due to this reason or due to this problem, we need to find a solution. So the solution for this problem is by using an ideal vapor compression refrigeration cycle, where later on we will explain in detail about this cycle.